All right, so example 12, we should be able to finish, even with the abbreviated time, we're in here till 2:20, so that's 30 more minutes. We should be able to get through the rest of this section. So when's the worksheet due if we finish today? Never. Very good, never. Right, right. But might we have another quiz tomorrow? Sure, yeah, right. Remember, your spirit is you come into class every day expecting a quiz. If we have one, you're elated. If we don't have one, you're disappointed. Okay? Right? Limits. All right, so this makes a fantastic multiple choice type question on either my exams or the ultimate AP exam. So let's have a look-see here. It's a piecewise function. Y'all are getting used to those. F of x is equal to that dude when x ain't 2, right? So that's a little bit different. That's not an inequality. So if it means x is not equal to 2, that means left of and right of, yes? So we're using the same function from the left and right of 2. So in this case, we wouldn't have to find a limit separately from both sides because it's the same function from both sides. But notice when x is 2, it's defined to be the letter k. So what are we going to do with that? Well, it says that that function is continuous for all x except at -0.5. And I'll explain why. Now it says to answer these questions, okay? What is the limit as x goes to -1/2 from the right? Well, which piece are we using when x is -1/2, the top or the bottom? Is -1/2 2 or not 2? It's not 2, so we're using the top, right? We're using the top piece everywhere except at 2, including way over there at -1/2. So let's go ahead and look at this x squared plus x minus 6 piece and 2x squared minus 3x minus 2. And let's just call that y equals. Let's see what that dude looks like or what he's accomplishing everywhere except at 2, right? And we did this kind of to start this section. There's a quadratic in the denominator, so there's up to 2 values of x where that function doesn't exist. We can find everything quickly by factoring. So let's go ahead and factor. The top is x plus 3, x minus 2, something like that. And the bottom is, well, let's see, nothing divides out, but it's going to be a 2x and a 1x. And then it looks like it's going to be a prime, so it's going to be a -2 and a +1. I think that would work because that gives you a -4 on the outside and a +1 on the inside, which does add up to -3. So hopefully factoring like that when the leading coefficient is not 1 is not too much of an obstacle for you. If it is, come see me. We can talk about methods, but Pre-Cal's doing that right now to review. So anyway, we have that. So what does that tell us? That tells us that if we were just looking at this, we know that x cannot equal what 2 values? 2 and -1/2. If you set both of those denominators equal to 0 and solve for x, you get those 2 values. Those give you division by 0, so the function's not defined there, which means, to review, they're both discontinuities. Well, we can figure out right here on this line if they're wholes or VAs, right? Pretty easily. The x minus 2's divide out. You can remove them. If you plugged a 2 in, you would get 0 over 0 because of those factors. So what do we have at 2? We have a whole. Good. And the other one, the 2x plus 1, we cannot remove it. And if you plugged a -1/2 into the top, you would get non-zero and 0 in the bottom. So that's going to be what? If you can't remove it or you get non-zero over 0, it's a vertical asymptote. Good. So that's review. That's like pre-cal stuff, but we've already done it this year. So we have 2 discontinuities. Okay. So this is a review from yesterday then. If I know that the function has a vertical asymptote at -1/2, I want to find the limit as we approach that vertical asymptote at -1/2 from the right-hand side. What do you know the answer is going to be? Some type of what? It's going to be some type of infinity. Okay? Some type. And we're going to come back here and figure out what the sign is. What's the safe free response answer? DNE would be fine and you'd be done. But for a one-sided limit at a vertical asymptote, we need to know if it's plus or minus. So how can we determine, without knowing what the graph looks like, if it's going up or down there? Plug in a number. Good. If we're approaching -0.5, if you will, from the right, what's the number just to the right of 0.5? Or -0.5, sorry. negative 0.4, right? So again, the rule of thumb is like a tenth away. So if I plug in a negative 0.4, you don't want to plug it into here. That's going to be too much work. Remember that once these are gone, you can use what's left over for the rest of the function, including how to find the y value of the whole at 2. So if you plug in that negative 0.4, which is just to the right of negative 0.5, what sign do you get? In the top, you get $3 minus 40 cents is positive, right? And in the bottom, 2 times negative 0.4 is negative 0.8. So what's $1 minus 80 cents? Still positive, right? Yeah, 20 cents. So when you plug in a number that's just to the right of negative 1/2 into what's left, you get positive over positive, which of course is positive. So that means that the answer is positive infinity. Okay, at the vertical asymptote. So that's what we did yesterday. How do we know there was a vertical asymptote at negative 1/2? Yeah, it gave us non-zero over 0, or that factor that caused the 0 on the bottom did not divide out. That's what you meant, Huey? Yeah, okay. If you wanted to figure out what the limit was from the left-hand side, you would just plug into that same thing we did, a negative 0.6, something to the left, and look at the sign. Okay, so I'm going to skip that. What would be the limit then as x goes to 1? That's the general limit. Do what? I heard it. 4/5? How'd you get that? Very good. If you remember, the only 2 places where we know this function is not continuous are at 2 and negative 1/2, then it must be continuous everywhere else, including at, where was I? Right here, including at 1. And so if we know the function's continuous at a point, we know its limit value is the same as its function value. So let's just find the function value. So I'll plug in a 1, and I can either use this piece here, which is fine, but we can also use what's left over right there, because it's going to be the exact same everywhere except 2. So if you plug in a 1 there, you get 3 plus 1 is 4 over 3, so 4/3. There you go. And that's not only the general limit, that's the limit from the left and right. So we talked about that yesterday. If you know the function's continuous at a point, direct substitution will work. The limit value and the function value are the same. Okay, now here is kind of where the multiple choice part would come in. This is the typical multiple choice question. What is the value of k? Well, let's go back and read the question. It says that this now piecewise function, which is that everywhere except 2 and is equal to k at 2, it's continuous everywhere except at negative 1/2. Well, that makes sense because negative 1/2 is a non-removable discontinuity. It can't be continuous there. But if that's the only place it's not continuous, we need to make it continuous at 2, don't we? We need to make it continuous at 2 because we just said there was a hole there. So here's what's happening. If I use this top piece everywhere except at 2, it's coming in like this, and it's doing that. Here's x equals 2. Okay, and what I need to do then is I need to figure out what is the y value of that hole so that I can explicitly define it to be that y value at 2 so I can plug the hole, right? So essentially, what do I need to find? I need to find the limit of that top piece as x approaches 2. That's what I need to find. I need to find the limit, right down here. I need to find the limit as x approaches 2 of the function f of x. So how do I do that? It's the same as the y value of the whole, right? That was our first quiz. The y value of the whole is the same as the limit there. And how do we find the y value of the whole? We plugged it in to what was left over once we got rid of it. So I'm going to plug a 2 into x plus 3 over 2x plus 1. And that gives me 5 over 5, which comes out to be 1. So if the limit is 1, I can say, so k must equal 1. And so now we're kind of like mathematical surgeons. You could think about this top piece as having a natural birth defect at x equals 2. It had a hole in its graph, okay, at x equals 2. I need to go in and find the y value of that hole at 2 so that I can come in and manually repair it, okay? And we just did that. Okay, so I've come back in here. I've identified that that needs to be at y equals 1. And now we can go there and plug the hole. There's still going to be a vertical asymptote at negative 1/2. But because that's the removable point discontinuity, we can redefine it there and make it continuous. Okay, so what did we essentially do? We had a piecewise function, and we found the y value of the whole, of the top piece, and we let that equal the value that we defined it to be at 2 to plug the hole. We factored, we divide out, and we plugged in. Okay, plus we reviewed on A and B. So that's a good question right there, like possibly free response. Good stuff for the whole thing. Maybe a multiple choice just for part C. All right, any comments or questions on that one? A little more abstract because we're not just testing something, we're actually finding something. Yeah? Okay. Sweet. Example 12. There's one last type of discontinuity that we talked about. Let's see. What are the ones we've talked about so far? We should probably review that. We just reviewed 2 of them on the previous problem. Removable, which we call holes. Non-removable infinite or vertical asymptotes. What was the other one that we talked about? Jumps, okay? Now, those are only going to come from like piecewise functions for now. So if it's a rational function, something over something, it's not going to be a jump. But there is a third one, or a fourth one, I should say, and it's not going to show up a lot. In fact, it's not on the AP exam. But it is kind of interesting. I want you to know it. And it can be a little tricky. Yeah, sweet, okay? It's called an oscillating discontinuity. Oscillating discontinuity. What does it mean to oscillate? Up and down, up and down, up and down, up and down, back and forth, right? What type of functions do that? Trig, right? Sine and cosine, trigonometric functions, they repeat. Yeah. So let's take a look at it. Example 13. This is how I'll introduce this discontinuity to you. It says to examine the function f of x equals sine of 1 over x in the vicinity of 0. All right, so if you're bold, right, it says in the vicinity of 0, let's just go straight to 0. Let's see what happens if I go stand right at x equals 0. What do I get when I plug in a 0? I get sine of 1 over 0. Uh-oh. Does that make sense? No. What is 1 over 0? It's undefined, right? Because graphically there's a what there if you get non-zero with 0? A vertical asymptote, which forces your y values to either positive or negative what? Infinity, yeah. So remember, the reciprocal of 0 is infinity, some type of infinity, and the reciprocal of infinity is 0. So whenever you get 1 over 0, it means the y values are going to infinity or negative infinity. And that's why it manifests as a vertical asymptote. So what would it mean then to take the sine of infinity or negative infinity? If you hopped on the graph of sine, here's just the graph of Sahala, and you went out forever and ever and ever, and you looked to see what the y values were doing, what would you say they were doing? They're oscillating, right? They're not going to like level off towards a value. They're not going to go to infinity. They're constantly oscillating between 1 and negative 1. So as far out as you go, you never know where it's going to be. It could be anywhere between negative 1 and 1, and it's never going to settle down and stop oscillating. So this would be undefined, or DNE. All right, so the function value doesn't exist there. We tried it. Can we still analyze the function in the vicinity of 0 then, if we can't actually go stand there? Absolutely, and that's the idea of the what? The limit, okay? So here's how we're going to sketch this one here. I'm going to sketch it with you. We're going to sketch the graph of f of x. All right, so think about, let's get rid of sine right here. And think about your sinusoidal functions back from pre-cal. The number in front is a 1, which means it's the amplitude, right? So this thing's going to still oscillate between 1 and negative 1. But remember when we affected the inside of the function, this affects the period. It affects the period / the frequency of the graph. It affects the frequency, okay? So what happens as x approaches 0? As x approaches 0, 1 over x approaches infinity, right? And remember, that was the number of cycles in 2 pi. So the number of cycles in 2 pi is approaching infinity. Oof. Let's see what that looks like. Here's 1. Here's negative 1. I'm just going to hop in somewhere right here. It's the graph of sine. I'm going to start oscillating towards x equals 0. But as I do, I need to start forcing in infinitely many numbers of cycles, which means to force infinitely many in, I have to start doing what? The period of each of them has to start getting smaller and smaller and smaller And in order to do that, it's going to have to start oscillating. The frequency increases, we say. So it starts to oscillate faster and faster and faster and faster. But am I going to ever reach zero? No, I'm not going to reach zero. It's going to continue to get closer and closer and closer and closer to the y-axis, all the while oscillating faster and faster and faster between -1, which I forgot to label, and +1. And it's never going to reach zero, much like a vertical asymptote. The graph never reaches it. Okay? And so by this analysis, if we take a pulse as we get closer and closer to zero, we never know where it's going to be. It could literally be anywhere between -1 and 1. What's going to happen as I do that from the other side? Same thing, right? It's going to continue to oscillate with a faster and faster frequency, and it's never going to reach zero. So it's going to just go up and down forever and ever and ever, and it will never reach zero from the left side. And by the same token, you can kind of take a pulse anywhere to the left of zero, and it could be literally anything between -1 and 1. So these two things are kind of bouncing up and down right in front of each other, and they're not necessarily even in sync with each other. They're never going to get tired and just say, hey, you want to stop this and meet up? Sure. And put an open circle there. It's never going to be a hole. Okay? They're never going to stop oscillating, so we can't even talk about a jump, right? If they ever stopped and they weren't the same, we could say, oh, there's a jump. It's not a jump. They never stop oscillating. And, of course, they don't go up to infinity or negative infinity. So that's why this is that fourth type. This is an oscillating discontinuity. They never stop oscillating, and they're getting closer and closer to each other. All right, so it's kind of interesting. Now let's look on the other end of this function, because this gets into section 1.3 when we start looking at end behavior, which is as x gets really, really big towards infinity. If as we approach zero, you can think of this kind of like as a spring that's being compressed. What happens then, alternatively, as we go out to the right? It does the opposite thing, right? The period starts getting longer, the frequency starts getting smaller, it starts to oscillate slower and slower. Well, we can go out forever and ever, and it's going to continue to oscillate slower and slower and slower. Will it ever continue? Will it ever stop oscillating? No, it'll never, ever, ever stop oscillating. Will it ever get to a point where you won't be able to see it oscillating anymore, though? Yeah, it's going to oscillate so slowly that it just looks like it's almost a flat line. But remember, this is infinity. It's kind of hard to think about eternity. So if you go way down the line, it's going to be in a different spot, but it's going to appear to be motionless. You can actually Google something called the black pitch experiment. I think that's what it's called. Or pitch drop, black pitch drop experiment. Have y'all seen that? And it's literally like in some kind of lab, and they have, I guess it's like this. And they have what's called pitch. It's like this tarry substance, and it's in this bowl, and it's kind of hanging on a table. And it has like this long booger that's hanging from that flask, okay? And here's the table. And it's been hanging there forever and ever and ever. And it's moving. And they have a camera on it, right? So that when they're not there, they can record it. And there's a live feed of it. And the goal is to see if you can ever catch the pitch to like break off and drop, okay? And it's like never going to happen, even though that thing is working its way closer and closer to the table. No one's ever seen it drop live. They caught it on camera once many, many years ago, but that's how long that thing takes through. It's very exciting if you're ever bored just to log in and watch the live feed. That's the same thing that's happening here. So my question to you is, if it does get to the point where it appears to stop oscillating, even though it still will be, it's going to look like a horizontal line, right? What horizontal line will it look like? Will it look like y equals 1, y equals 0, y equals -1, or something else? Would it look like it is at 0? I like that. Why you say 0? It's perfectly in between -1 and 1, yeah? So if you think about pulling this spring and you grab it on the x-axis, and it's never tethered on this end, yeah, you can see that it gets pulled maybe towards 0. We can actually approve that. Cosine wouldn't do that, but sine would. Here's how we do that. If you think about 1 over x, what is this limit? We did this in pre-cal, and we're going to do this again in 1.3. What would be the limit as x goes to infinity of 1 over x? In other words, what's happening on the inside? As x gets really, really big, what's the reciprocal of x doing? Getting really, really small, approaching what? 0, right? 1 over 10, 1 over 100, 1 over a million, 1 over a zillion. That's getting really, really small, approaching 0. So as you go out to the right, this function is approaching sine of 0, because this approaches 0. And what is sine of 0? 0. So yes, it's weird. You start thinking about infinity. On the one hand, it's going to oscillate forever and ever and ever and ever and never stop going between -1 and 1, but at some point it's going to appear that it is pooped out and is lying on the x-axis, even though it's still oscillating between -1 and 1. You'll never see it move off the x-axis, even though that will move up and down between -1 and 1. We'll just never see it. Is that weird? That's very weird. Is that cool? Kind of cool. Yeah, it's kind of cool. Okay, so that's why I bring this to you, just because it's one of those, when you start dealing with infinity, you start dealing with like paradoxes, okay? And if you ever go on to take Cal 2 or BC Cal, at the end of the year, there's some really paradoxical sequences in series, okay? So this is kind of a taste of some of the strange things that happen at infinity. All right, so just to summarize here, to finish up, we have, 8 minutes. When you cover up an x value, like at x equals c, when you don't care what happens underneath that red strip at x equals c, and you only concern yourself with what's happening as you approach it from both sides, those are the roads. Those are tantamount to the limits, right? We don't care what's happening under the c. The function could be defined. It could plug the hole. It could be somewhere else. I don't care. Those are the limits. However, when you put on shutters to the left and right, and you only concern yourself with that specific vertical location, that's the idea of the bridge. And that's the idea of the function value from Algebra 1, Algebra 2. That's the function value. Okay? It's only when you remove the red strip and the shutters on either side that you get the full picture of what's going on in the neighborhood of x equals c. Okay? And so that's what makes this class different. We're not just analyzing at a point, we're analyzing in the neighborhood of, okay? And that's where the limit and the function value make a great team, because now we know that the function value and the limit value don't have to be the same. They don't even have to exist. So in this case, the limit would exist and the function value would exist, but they're different values, right? And so what type of discontinuity would this one be? It would be a hole, right? And it would be a hole at whatever this y value is up here. Okay? So again, just to clarify, they're both y values. Limits are y values, function values are y values, but the limits are the roads leading in, and the function value is the bridge. Okay, so finish this. I'll give you like 3 minutes to do this, and then we'll look at the answers. This is a great way for me to ask certain types of questions. You have this ginormous graph here called graphus interruptus, which is Latin for interrupted graph. Go ahead and go down the left side and just quickly see if you can pull off these values from that graph, okay? And I'll do it as well, and we'll compare answers. Hopefully I'm as smart as y'all. Try to be as, give as much information as possible. I can leave that up there if you don't. You can scroll back and forth as easy as I can, but there's some of them labeled. There might be test questions, either on mine or AP, where you are just given a graph like this, and you're just asked to pull a limit or a function value off of the graph. All right, 30 more seconds and we'll see how you did. All right, so at -2, there's a vertical asymptote. The graph is going up on both sides. So positive infinity is the preferred answer. That would be the multiple choice answer. D and E is also a safe answer for free response. 2 from the left, that's the road. The answer is 5. The function value at 4, that's the dot, that's 5. The general limit at 4 is also 5. It's continuous there. So the limit is the same as the function value. And so we could say, based on these two, that the function's continuous at 4. Okay, good. From the right of 11, that's coming in like this from the top. You're approaching this open circle. That's at 5. From the left of 5, okay, so here's 5. As you approach from the left of 5, it's going up, 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 up to infinity. So infinity is a better answer because it's a one-sided limit. A D and E would work. F of 2, okay, so there's a lot going on at 2. F of 2 is the dot. That's at 4. So that's the function value. From the right of 6, that's coming in right here, and you're approaching that open circle, which is at 3. So that's letter H. Letter I, from the left of 6, you're coming in from the vertical asymptote, and you're approaching the solid dot, which is at 2. So that's letter I. J is the general limit at 8. So you got to look at both sides now. The limit from the left and the limit from the right, they're both approaching the same Y value. It happens to be the Y value of the whole. So the general limit exists, and it is 3. Okay. The function value there is 5. That's the dot, but the limit exists as 3. F of -2. Now this is crazy. Notice there is a dot on the vertical asymptote. This would come from some piecewise definition. Okay. Normally for a regular function, we don't have anything defined at a vertical asymptote. But with a piecewise function, we can define it however we want. So there is a dot there. It is -2. I'm sorry, +2. And then the limit from the left of 0, that one hopefully is pretty easy. You just approach 0 from the left, and you're approaching the dot, which is at 2. So there you go. You got them all right? Well done. If you need to go over some stuff, I'll be here in the morning at 8. We're going to start the next section tomorrow. So have a great afternoon.